So what's happening there? Well, kind of what's happening is that instead of a Cartesian coordinate system, instead of orthogonal axes, we're going to use radial axes. Axes that now with these 4 dimensions, they're going to be equiangular apart. So now if I want to figure out where would I plot a point, well, how would I do it? If I want to look at a particular flower, I know it's got some sepal length, some sepal width, some petal length, some petal width. So I'm going to just have to mark them on each one of these axes. And that means I'm going to have some kind of shape. Okay? So I imagine that I'm going to have the minimum value of my data set being at the center, the maximum value being out here. So this particular flower has that sepal width and that sepal length. So it becomes a line segment. Okay, those are the 2 points. And if I have all 4 measurements, I've got some sort of shape. So that's one of the flowers. That's one data point. Okay? It's one of the setoses, actually. Here are all of the setoses plotted on top of each other. They seem to kind of have this same sort of shape, right? And you might ask, are these variates correlated? So if you had Cartesian coordinate systems and you had 2 orthogonal axes, right, you'd be looking at a correlation is, a positive correlation looks something like that, the data points. As one is small, the other seems to be small. When one is large, the other seems to be large, right? So you see this positive correlation. What does positive correlation correspond to in this axis system? Yeah? Yeah, like they all move out together. So this sort of thing that you've got high with high, that's kind of a positive correlation. What would a negative correlation look like? Well, in a Cartesian coordinate system, what would it look like? It'd be this sort of thing, right? The scatter plot's going from northwest down to southeast. Yeah. Wouldn't it all just move together except in a different way? Don't get technical with me. So they'd all look the same, but wouldn't look like that. But it'd be high with low, low with high, right? So you should see, if I have a high value here on that particular flower, I should have a low value. High, low, and as this gets lower, this should be getting higher. Did you ever do that string art when you were a kid? You should see some kind of curvature here. So this looks like there may be a bit of a negative correlation here. We want to see high with low, low with high. And if they were perfectly correlated, you'd see a beautiful little curve, yes? If it's negatively correlated, so the problem with this particular set of flowers is this length of this axis is determined by all 3 species. But if this were all the way out here, I'd see that, 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 that. It would go like that. So I'd see kind of this curve. Right? If you do the so if you imagine just 2 of these axes, high with low, that's sort of a perfect negative correlation. So you'd see this kind of curvature. High with high positive correlation. Right, low with low, high with high. Okay, makes sense? So you can look at this and at least get some sense if there hasn't been too much over plotting that you can't tell what's going on, of how pairs of variates are correlated. So this is the versicolor, which definitely looks a different shape than that. And you can think about the correlations. They're very positive correlations, and maybe there's not quite so positive here because you see some going down below. This one looks a little more positive. And there's Virginica, again, which looks a lot like versicolor, but bigger. Okay, so Virginica, versicolor, setosa. Setosa looks quite different from the other two. All right. So that's a four-dimensional representation, yes? So if only three of them were correlated, so you have to, it has to be kind of tricky that you've got these correlated, this is correlated, that's correlated, that's correlated, and these two are not. So you have to construct that pretty carefully because the correlation of going along here suggests that these two will be correlated as well. Each quadrant is just one pair of variates. You're looking at the correlation. Okay. So there they are, the three different species, and you can see the differences and the similarities. Now, if I didn't know which species they were, it'd probably be very easy to pick these guys as different. Separating these two, it's hard to tell because this kind of nests inside that one. It's not that different a shape. Okay. Here are the averages, and I've chosen to fill these in. So I've filled in the whole star here so you can see the shape of the average. And this doesn't look quite as nice as Anderson's with, you know, one being nicely 1/3 of the way along. How did that happen? It's curious that it happened at the same time I waved my hand and I wasn't even touching the trackpad. Okay. So there the three averages are, and there the three overplotted, so you can see them with the alpha blending. So we've got the averages, and I can see it's almost like an analysis of variance now. I can think about what's the difference, is this difference in the averages much greater than this differences between individuals within each group, right? Okay, probably that's a good spot to stop. Pick it up next day. So have a look at the size of the petal for each flower. And there are three different species. So when we map this, we take for any particular flower, we find its value of sepal length and sepal width and mark that on those two axes and draw a line joining those 2 points on the axes. And we do that for all four measurements. So what happens is that every one of these points in 4 dimensions becomes a shape on the 2-dimensional plane. And the shape's defined by these its position on these equal angular axes. So we looked at this last day, and those are the shapes of all of the flowers that are of the species Iris setosa. You see they seem to have a common kind of inverted kite shape here. And this is versicolor, all of the versicolor. Again, we did this last day, and all of Virginica. and asked you to think about how do correlations show up. And the correlations, you recall, are measurements between two variates, just how they vary together, how they co-vary. Right, so it's going to be, that's why there's a covariance involved, divided by the relevant standard deviations to give you the correlation. So the three species overlap look like that, and you can see immediately once that the Setosa is quite different from the other two. Versicolor and Virginica are same in the shape, whatever that means, and they are principally different in size, and that the Virginicas are much larger than the versicolors, and the Setosas are the smallest of them all, although they do seem to have very large sepal width. Okay. These are the averages that we filled in, just so you can see the shape itself, and all of these together. So we can think about the variation in averages, just like Anderson did, in terms of those glyphs that were natural for this particular data set, but now with a more general approach. So we can see them, all the averages and how they appear together. The averages, think about an analysis of variance. Analysis of variance where we are often comparing the group means, the group averages. So the average in this group, the average in that group, the average in this group. How do they change from one another compared to the variation within groups? So that's often a comparison, variation between groups compared to the variation within groups, if there's a significant difference. Okay, so we've done all of this, so we're looking at the stars. The stars is how command is how we're generating these in R. And I believe I looked at all of these. These are all 150 now, which you might think about using these shapes to cluster. So looking at which shapes seem to be alike, most alike, and it certainly would easily group the smallest ones, and these small ones, as we know, are all the Setosas. And then you start thinking about grouping these other larger ones by shape and size. So you might imagine how would you order these if you're to be able to rearrange them on the page. So that's in random order. Having the axes appear as well is very handy for the principal reason is that you do get to see where the origin is, where the center is, and consequently where the large values of. This shape by itself, without the axes there, you don't know that it's very long on this particular variate and short on the other, particularly if that were little more symmetric looking. This is it with filled in colors. I can't remember. Have we passed where we were last time? No? So we still covered this. So again, you're looking at different clusterings by shape. All right, so what's kind of interesting is if you have those shapes, that's representing the higher dimensional data. And it might be interesting to look at positioning those just like we positioned glyphs on a map, like Galton did with the weather maps that he was looking at, or any of the weather maps. So you just position these glyphs on a map where now the map is really just two of the variates themselves. Okay. So when I locate these on a plot by two of the variates, it becomes a lot easier to see the grouping. So I'm seeing the grouping in this two-dimensional space of this group here. There seems to be a cluster of values of points in this area here, but also every point in that cluster seems to be roughly the same kind of shape. So they're kind of closer to each other in the four-dimensional space as well. Again, it looks like another giant group here that has separated from this group here, which is Setosa, and it has glyphs that look an awful lot alike. If they're going to separate at all, they're going to separate largely in the size of these glyphs. And you can see that the glyphs up at the top right here seem to be larger than the glyphs at the bottom left. And perhaps there are some that have different kinds of shapes here. So larger up here, and then you've got these kind of kite shapes and the little square shapes. So you might think about how would you group those. So it's kind of fun to think about looking at these glyphs and pretending you don't know which are the species, or even how many species there are, and just trying to group them together visually. That is, visually cluster them. How well do you do in identifying the known groups? Okay. Any questions? So the stars are pretty interesting that way. Here's the higher dimensional data set. So this is the olive data, which you recall has 8 dimensions. And the interesting thing here now is we've got 8 axes. So the axes you see around the bottom here, these are the 8 fatty acids as they appear in the data, and the measurement on each of those will produce a shape for each of the olive oils. So now you look at that and start to think about visual clustering. Which of these shapes look alike? If the shapes are identical, they occupy exactly the same point in an 8-dimensional space. Right? If they're the same shape but different sizes, they're almost lined up, moving away from the origin in an 8-dimensional space. Because all that's changing is the size of the glyph, not the shape. Okay? So you start to group these as ones that look most alike. And some of them are kind of easy. You might group this guy, perhaps, and this guy. And you might find maybe this guy should go in that group. Over here, another one. Some of these are going to be fairly easy to identify as possibly from the same region. So again, in exercise, you're going through these, and especially if you could move these around dynamically, which you could in Loon if they were glyphs in Loon, move them around on the scatter plot and group them so that you can put them spatially in places where the glyphs look an awful lot alike. Okay? So we now have roughly, are they neighbors near each other in an 8-dimensional space? Okay. Any questions? So if I locate these on a plot, so I use 2 of the axes, and I've got alpha blending here because there's a lot of overstriking. I locate them according to a couple of the variates and just put all of the glyphs. So this is just like, again, our weather map, but we're using glyphs that are meaningful about the higher dimensional structure. And sure enough, you see that these 2 variates are actually grouping some of these groups spatially. So you may see these little, I don't know what these are, mosquitoes or something, or butterflies up in the bottom left corner that seem to be a similar shape. This group up here that seems to be located along a ray here that is roughly the same shape. Bunches over here that are the same shape. So not only are these points near each other in this particular 2-dimensional projection, but they're close to each other in all the 8 dimensions. Okay? Make sense? All right, and if you saw, for example, if we saw this group over here that looked an awful lot like that, and one of these guys over here, they would stand out as a stranger in the crowd. Much like those turn-off faces where you see somebody that looks very different from the others, but now we've got just this geometric shape. Okay, so let's think about correlation. So this is a completely artificial data set where I've just introduced some correlation. There are 4 variates here, W, X, Y, and Z. And the correlations are as in this table. So the correlation between X and Y is 1, between Y and Z is -1, and something nearer zero between W and X and Z and W. And the axes are W, X, Y, Z going counterclockwise beginning at the horizontal one. So X and Y are strongly positively correlated, correlation 1. And how does that manifest itself? Well, if we look at the XY, that's this top left corner, this top left quadrant. And now look across all of these glyphs, and you'll see that that's a nice isosceles triangle, right? They have equal lengths on both sides across all of these glyphs. Sometimes it's very small, but it's still nevertheless there. That's the positive correlation. And Y and Z, that's that bottom left corner, that bottom left quadrant. You'll notice that it's really squashed, this sort of scalene triangle, where if you have a large value of Y, you often have a small value of Z. It's perfect correlation here. And if you have a small value of Y, like here, you give a large value of Z. So that's a negative correlation. Okay? So if you've got correlated variables, you expect to see certain patterns in the stars themselves. If you overlay those, it's a lot easier to see what's happening. We talked about this briefly last day. So X and Y have a perfect correlation. Look at those beautiful, perfectly parallel lines. Okay, that's a +1 correlation. There's a -1 correlation. So you're going to see that kind of curvature in there when there's a negative correlation. This convexity, roughly speaking, when there's a positive correlation. So if you look at these two pieces where you have effectively close to 0 correlation, it's all a bit of a jumble. Right, there's a 0.03 is the correlation on either one. One of them's positive and one of them's negative. And even with that smaller correlation, you can get some suggestion with this overlay that if I had to choose which of these two was positive and which was negative, I might be thinking about where's the bulk of this data? Does this look like it's more horizontal, or has it got some kind of curvature inside there? So W and X was our negative correlation, near 0. W and Z was our positive correlation. So that's our negative correlation. You can see a bit of the crisscross, little thinness out here, not so much here. This is more positive and near 0 correlation. Okay? So just seeing the patterns and understanding the patterns in those line segments, you can at least look at pairwise correlations between the variates. Any questions? Yes? So here are the most dramatic ones, okay? But look, but I want you to look at these. This is the most dramatic one. So you see that this nice convexity out here, they're just sort of filling out the whole thing. And you see this negative one, you've got this lovely concavity moving in there. Now when I'm looking at these are near 0, so I expect to see some that are high with low, some that are high with high, etc. And on both of these, they're near 0. However, even in this case, I'd venture to say that I seem to see a little thinness here, and then I see more concavity here than I do in this one. Okay? So I would guess, if I had to guess, I'd say that was the negative one, and that was the positive one, but they're both close to 0. Okay? Yeah, it's just that curvature that you're looking at, which is, admit, it's barely there, right? But it looks a little bit more there than here, just because of this thinning out. But they're both so close to 0 that they're darn near the same. Yes? That's correct. You cannot see the correlation between Y and W. I mean, you might try to guess what that is by following these lines, etc., but it'd be very painful, right? That's a real problem with these star glyphs, right? It depends on which variates are beside each other, which correlations you see. So, so if you think about the difference between these radial axes and the Cartesian coordinates, the Cartesian coordinates had to have orthogonality all the time, which only works up to 3 dimensions. Not so good beyond 3 dimensions, at least for visualizing. Works mathematically just fine, but not for actually trying to draw the thing. This radial axis, the axes appear in series. So the order kind of matters, because you only see one axis beside 2 others, its neighbors. So what we want to worry about are the effects of that order. And we've seen that before in the past. Right? When we're looking at comparing distributions, we're thinking about the order in which the comparisons were made. So we know one way to get around that, and that would be by repeating the axes and maybe making sure that every axis appears beside every other axis, so at least you see every pair. So you will see W and Y in somewhere. And we know how to do that. That's our graph theory, where now every axis is a node of the graph. We look at the complete graph and think about traversing that according to an Eulerian. Okay? So every path on there is a selection of the order of the variates of the axes, and an Eulerian will have every pair appear beside each other. Hamiltonian is going to have just particular pairs, but every axis will appear once. And if we have some measure like correlation that we think is an important thing to have, we could order the axes so that high correlation ones appeared beside each other more frequently than others. We're still stuck with the fact that it's a greedy method, greedy Eulerian method, or that it's if you're stuck with a Hamiltonian, that you're looking at all axes appearing exactly once. So these choices could affect this displays differently. So for that 4-dimensional data set, here is the Eulerian, and you'll see that X, Y, W, and Z, right, all appear more than once. So now I can see the X-Y correlation. It appears twice here. But I can start to think about what's the W and Y correlation, which I didn't see before. And again, that looks kind of negative, that correlation. So I've repeated the axes, and I get to see all pairs now. Okay? Any question on how that would be constructed, or this interpretation? Okay, so you can easily use the same technology we've used before to look at have all pairs of axes appear beside each other. So every axis appears beside every other axis. So at least you've gotten rid of that effect of that, what I see depends on how the axes appeared. That said, the different orders may be better than others, right? Particularly if we don't want to look at all axes, but just look at the most important ones. So all of the usual rules, if we had some way of measuring interestingness, might be a way of ordering the axes. So on the iris data, here's what the iris data now looks like, where I've got the Eulerian. So I have many more axes now. I've got 1, 2, 3, 4, 5, 6, 7, 8 axes. And the shapes, again, Satosa is pretty easy to tell, these little daggers that are here. And you may have now, because every variate appears beside each other, you're not going to be missing a pair of variates that will distinguish the species from one another that might have been missing before. Okay, so you do the same sort of exercise and group shapes, group these into different groups into 3 groups, and see how well you do. See whether this is an improvement over the previous one. So you can imagine doing experiments on humans to see which of these is a better representation. Any questions? Okay, now if I do a higher dimensional thing, the number of axes here is going to be, I want to see all pairs between. If I look at the olive data and I look at pairs, now I'm getting really interesting glyphs, these sort of glyphs that are spiky, or some are very convex depending on it, so I can, depending on where they are in the 8-dimensional space. So these are still points in 8-dimensional space, and I might think about grouping them together. So if I look at this one in particular, I might see others that look a bit like that, like this one, right? Like this one over here. And then these that maybe look a little bit more like the poppy I'm wearing. Is there something like this? Should that be grouped with that one? At least you'll find out, are they neighbors in this higher dimensional space? Again, using the glyphs and just the shapes. It's hard to tell anything more about them rather than are they near each other. Okay? Any questions? So far, so good? Okay. Just with the stars data, that was having everything was from minimum to max over the whole data set. You might like to choose to have the scales be exactly what the data had. So rather than having the min and the max appear, have just whatever rather than have them scaled to the max over the whole data set, we could have them scaled, for example, to each of the individual flowers. So what I've done here, what's happening here is I've rescaled all of the individual flowers, right, to have a 0, 0, 1 scale. And that means the relative size of the flowers is going to be gone. I'm not going to look at different sizes of flowers, and we'll see that the scaling is false. So first look at the case when I've got no repetition of variance. So here, what I've taken out is the differences in the sizes of the flowers. So I'm interested, if you think about a high dimensional space, if you had the same shape, if you're going out on a line out from the origin, right, everything's increasing at the same rate, right? So that shape is kind of maintaining its shape, all of its relative proportions. It's just getting larger. So I've taken that away. So I'm trying to say, are they all roughly in the same direction or not? And again, you'll see now Setosa is not distinguished so much by its size, but rather by its shape. So you can see these are all off in a particular direction, and versicolor and virginica are much more alike because their principal difference was the size. Okay? So for some problems, you may want to be doing this, sort of scaling by, so that we've removed the effect of the size of the species. Okay? And on the repeated axes, it looks a lot like this. And again, we're looking at roughly the shapes of the flowers. And you see Setosa being much different from versicolor and virginica. Versicolor and virginica being more alike, but some differences again of versicolor largely in this pair of coordinates up here, which are quite tiny for most of versicolor. Sorry, virginica. Virginica is the purple one. Okay. So all kinds of things you can do with these glyphs depending on the context and what you're interested in comparing. Any questions? So one of the interesting things about this axis system is we've gone from a high-dimensional Cartesian axis system, which we can't represent on the screen, to a two-dimensional version of it. We've done that by making these equiangular radial axes. Well, you could lay them out as well in parallel. So an alternative is just to lay these out across the page or the screen as parallel axes and do the same trick. Just find out where each point is located, its value on each of these variables, and connect them. Okay? And this is called a parallel coordinate plot. And it's very, very popular visualization plot. Due to the mathematics, you see a lot about it by Al Inselberg. It's also popularized in statistics by a fellow named Wegman. So here we go. There's one flower now. So what we've done is we've turned this four-dimensional point into a curve. It's more obviously a curve now because we're just having it go across the page. So this particular flower had a low sepal length, small sepal length. somewhere have a sepal width towards the middle, a very small petal length, and a very small petal width. But that's one flower. Okay? So here's all of Iris setosa flowers. And you can see they seem to follow a very similar trajectory across the page. This guy is an oddball. One good thing about this, you can see some of the strange points. This guy's got an unusually small sepal width on this one dimension at least. You can see them following roughly the same pattern with spreading out here and then pinching down here, and they're all down at this value. You can also see a bit of the granularity of the data here as you see these pinch points that there are in fact only 1, 2, 3, 4, 5, 6 different petal widths for this thing. Okay. Also think about what is correlation. Well, correlation within this group, just for setosa alone, it looks like the lines are kind of going up together here. They seem to go together, high values with high values, low values with low values. Same here, low values with the lower values, high values with the higher values. Positive correlations. Okay? High with high, low with low, positive correlations, which you're tending to see. Get more into that in a minute. Here's versicolor, and you see that's a rather different grouping. So we'll see they're nowhere near down on these small petal width and petal length. There's this nice grouping that's going across the display. And you might imagine that when we look at virginica, which are the larger ones, it's going to occupy more of the top, principally on the petal size. And think about what would a low correlation, what would negative correlation be? Well, negative correlation is going to be high values with low values with high values. So you're going to see a lot of crisscrossing when you've got negative correlations. Okay? So altogether, when they're overlaid like that, it looks like that there's just a lot of sticks down here, but you can see I've got identified it with colors because we know the groups, but if you didn't know the groups, you would certainly still separate out this pink group from the other two. And these, as we've seen before, are largely ordered by size. Okay. So just the patterns that we can see there in that set of parallel coordinates allows us to distinguish at least some of the groups. Make sense? So you see pairwise correlations and distinguished groups. It's very similar to the the radial axes, arguably a little easier to see correlations. Okay. Any questions? Yes. Parallel, you mean? They're all straight, all lines are straight. So you mean, are they parallel? Parallel? That's going to be a positive correlation. Yeah, so you think about where does it start and where does it end? So the highest of the pink here seem to be on the highest of the pink there. The lowest of the pink here seem to be on the lowest of the pink there. Low with low, high with high, positive correlation. And if where they were truly parallel, you'd see that across the whole, all of the pink ones. I mean horizontal, because they're all straight. So parallel is some kind of correlation, positive correlation that you're seeing, and at least all in the same direction in positive correlation. I'll make this more precise in a minute. If they're parallel, that means they're matching exactly on the range. Don't forget the range of these axes is determined by all three species. If I drew only setosa and had this scale to follow setosa, those pink lines would look almost horizontal. Okay? Yes? No. Min and max, typically. I mean, you can have them whatever you want, but the default would be from minimum to the maximum in the data. That's why you see at the very top there's always a point, and at the very bottom there's always a point. It's just the min and max is over the whole data set. So that allows us to see the petal width for Setosa to concentrate down at the bottom here. If I did min and max differently, you know, so that within each species, I'd want to be seeing, does that species look the same in roughly its proportions or its in correlations? Okay. Other questions? This gets a little more fun as it, when we do, I'll do it in a minute, you'll see it, so give you a little more insight. So here we're using an Eulerian, right? So we've got all pairs of variates, which means some of these variates are repeated. So sepal width appears there and sepal width appears there, for example, so that every pair of variates appears next to each other. So if there's a particular pair where they really separate it, we'll be able to see it much better since we can look at all of them. Okay? Everybody understand this picture? Same as before, except now every pair appears. Okay? So, this is where it's going to get interesting. It's kind of a dense slide here. But there's in fact a lovely connection between parallel coordinates and Cartesian coordinates. Lovely mathematical connection. And this is called a line point duality, in the sense that we saw when we did parallel coordinates, just think of two axes, a point on a plane, right? So it has two coordinates. That's a point on a plane, gets a point on each of the two parallel axes and turned into a line, right? So points become lines. And conversely, if there's a line in the plane, that will become a point on the parallel axis system. Now, you don't know what I mean by that as a point on the parallel axis system, but you will momentarily. So, this is answering some of the questions you were raising earlier about parallel coordinate points. And I think it's probably best if this is demonstrated. So I'm going to demonstrate this in Loon. So I'll go back to here and I'll just switch over here. So what we have in Loon here is we've got a scatter plot in this window and a parallel coordinate plot in this window. So these are two different representations of the same data. And if I look at a single point here, selecting it, that corresponds, that point is a line over here. All of these points in this 2D plane are a line, and you can see they all converge on a single point. This is easy because they're a line that they all have the same x. So on that axis, it's going to converge on a particular point. Okay? Everybody get that? So I've got a whole bunch of other examples here, so let me just reactivate them here and pick another one. So let's pick this guy and invert. Well, you can see that pretty easily and deactivate the rest. So now there's a line in the two-dimensional Cartesian system going from there, which turns into a point. A point being the point of intersection of these lines. So a line in 2D Cartesian systems becomes a point of intersection in the parallel coordinate plot. Okay. Well, why is that interesting? Well, it's interesting because if you see this in a parallel coordinate thing, you know it's on a line. All of those points are on a line. watch what happens. So if I take these selected points now, and I move these around, they're also on a line. They have a point of intersection. Watch that point of intersection. How does it relate to the other point of intersection? It's always exactly above it. So when I see 2 points of intersection over here that are exactly above one another, that's 2 parallel lines in the Cartesian system. Okay? So there's this duality between the two systems. So you can do a lot of familiar geometry on this side, and there's a corresponding pretty geometry on the other side. Whoops. That moves around. So parallel lines are going to have points of intersection that are directly above one another. Okay? Just put these back in place. Let's see what else I have here. Reactivate. So these green guys. Invert. Deactivate. So there's everybody's on a line. And if I move this around, blast. Pull this down. So if I move this around, you'll see that there's no point of intersection. That's still a line in the Cartesian coordinate system, but there's no point of intersection that I see in the parallel coordinate. What's happening is that point of intersection is happening past this axis. All of those lines are converging to a point that's just beyond the axis. So when you see something like that these guys seem to be converging off to one axis or another, you've got a line with a positive slope. Okay? And again, if I take a subset of these guys and move them around, let me just roughly half. And move these around. Right? They're still a parallel line, that their points of intersection, they still converge to 2 different points of intersection, but over to the right of that axis they'll line up on top of each other. Okay? So that's a little harder to tell that you've got parallel lines, because you have to imagine the point of convergence. So when you're putting out parallel coordinate plots, sometimes it's easiest to think about, well, what's a positive line? That's kind of like corresponds to a correlation of 1. Right, a positive slope line. Negative slope line, the correlation of -1. It's often easier to see patterns, at least this kind of geometry, when you've got correlation. You organize the variates, maybe by flipping one or the other, so that the correlation is negative. Then you'll be able to see the patterns a little better. All right, let's see what else I have. Select everything, put it back to where it was. Let's select this one and just jitter it a little. So what's happening? They're near a line. They're not exactly on a line. They're not all converging exactly at the same point, but the point they're converging at is every pair of lines over here is close to the others. So that's a correlation that's not quite 1, but that's still a pretty high correlation. You can see a positive correlation. They're all going off in a particular direction. Okay. Any questions? And of course, this gets much harder to imagine that these groups both have roughly the same correlation, but they're it's hard to tell that the place where these lines are approximately converging in the purple group and in the green group are sort of above each other beyond that axis. Okay. Note also that now if I look at this whole collection of points here, right, that's a negatively correlated group altogether the way they're arranged here, right? That there seems to be going down. I can move these a little closer, so negatively correlated as an entire group. And that's showing up here as this crisscrossing. So that group is negatively correlated, but any of these subgroups seem to be positively correlated. And so you might want to, identify them over here, select them with a brush on the lines, and see that it's in fact the same group. Okay, stop me if you have a question. So put those back where they were and get everything back. What haven't I done? Well, let's look at that, actually, not that one. It's a negative one. This purple one, there's a negative one. Just because I should have jittered that one. So if I select these guys, they intersect, the negative correlation intersects at a point there, and I jitter these. You can see that that's close to a line. Close to a line, close to a point. Okay. This line point duality. Put those back. I guess the last thing I'd like to do on this particular example is, if I can recognize the colors. There we go. Here's a parabola. And what do you see over on the right-hand side? You see this lovely curvature. Now think about what happens. I mean, as we're moving along, seeing this curvature here, what we're seeing are the points of intersection between these various lines, right? Between each pair of lines. Think about the lines formed here, right? That's a positive slope. They're nearly on a line of positive slope. They're roughly converging at some point. These guys are on a negative slope. They're nearly in the same position here. We're kind of tracking the tangent along this curve. And that's what we're seeing here. So if I looked at this bit here, that's that lovely tangent there. They're very nearly on a line. So you've got all of this stuff with conics that transfer over. Now, of course, real data is a little nastier. Not a mathematical object like that. And so it's almost on a parabola. Okay. Any questions? So think about where's the tangent. Think of a group here. You know, if we're following a line that seems to be roughly changing its slope, it may appear on the right as a sort of a curve through the space. So you can put those back in place. Nice paraboloid. We could look at actually correlated data here. So here's something we know to have 0.9 correlation. And This is nearly to your parallel axes, right? A 0.9 correlation. You can see these up here our points are very nearly parallel. Right, there's the top half of the data, the bottom half of the data. Nearly parallel all throughout. Parallel and horizontal in this case, because they're on the same range. Let's look at 0.5 correlation. 0.5 correlation, not nearly as strong, and you can see a little more crossover here. Let me just get the other one up here. So 0.9 and 0.5. So much stronger pattern here of near parallel, or at least going in the same direction, than there is here with the negative correlation. We saw that when we jittered as well. Okay. And more interesting again is the negative side. Well, let's just do zero correlation first. Zero correlation, some of them are high with high, some are like these high ones with high ones, some are low with low. That looks like it's a zero correlation here, a little hard to tell here. There's a lot of parallel and a lot of crisscrossing. If we go to negative, a negative 0.9, so we're running out of time. Oops. Minus 0.9, right? Nice little bundle. Sheaf of wheat across here. Okay, nice little bundle of sticks. And 0.5, negative, not quite as strong, not as tight. Because remember, if they were all exactly on a line of 1, these would converge at a single point. So the depth of this thing is giving you some sense of the size of the negative correlation. So not as correlated as that. Okay? Make sense? All right, we'll pick it up from there next day. But so those are parallel coordinates and radial coordinates, and we could do the same thing with the radial coordinates connecting Cartesian coordinates, but it's not nearly as obvious. Just to remind you, the key items here is that in the two-dimensional Cartesian coordinate system, that is a point in a scatter plot, turns into a line, or line segment, a line actually, in a parallel coordinate plot. And a line in a scatter plot turns into a point in the parallel coordinate system. Now that point it'll be the point of intersection of a bunch of lines in the parallel coordinate system. And those will either occur between the coordinates, between the axes, or they won't. So if they're between the axes, that's typically with a negative slope. And we'll see a cross between the axes. Crosses above one another, those are parallel lines. And if it's a positive slope, it's going to appear as a point of intersection beyond one of the two axes. And if those two axes, if that's all the data are on the same positive slope thing, the two axes, you'll have completely parallel lines. So in some sense, the point of intersection is at infinity when they're scaled that way. So completely parallel lines is a point at infinity. Right, you can't interpret, lines with common intercepts in a scatter plot do not produce points of intersections in the parallel coordinate plot at the same vertical location. The changing in the slope moves things around in the horizontal and vertical position. And a curve, you see a nice smooth curve like a conic in a two-dimensional Cartesian system will look very much like a curve in the parallel coordinate system, and that's largely because you're following tangent lines around that conic. So think about where the lines would appear, and those that are negatively sloped will have points of intersection between the axes, and those that are positively sloped will be intersecting outside of the axes. But you see this nice curve. And I encourage you to go through this demo that we did last day in class yourself and play around so you really get driven home that line point duality. So you should be able to just capture that behavior with this code that's on the course website. Okay. Whoops. So continuing on. So we're looking at it, you know, the iris data, looking at the 4 measurements, nice parallel coordinate system. You can see a negative correlation here with the crisscrossing on all of the data, negative correlation here on all of the things, but positive correlation within any one of the groups. And on the olive data, again, you see I've colored them by the regions, so you start to see some patterns in the data. Thing to note, by the way, is I'm using parcoord in both of these, so that's a function inside R to get parallel coordinates. So you can see the different areas, the regions, and the geographic areas within the regions of those olive oils are kind of grouping together across this space. And this space is an 8-dimensional space that we've now laid out in 2 dimensions. And so if they're close together and all across the whole plot, if that curve seems to be tightly bundled, then they're certainly near each other in that 8-dimensional space. So it's sometimes good for identifying clusters. Okay? Now that's where you know the answer. So let me have a look at this artificial structure. And think about that before you read the bottom line. This is some structure in 7-dimensional space. You should be able to figure out what that is. And what are the rules? Well, I've got a perfectly negative correlation here. Points are all on a line. 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 It's just positive, negative slope, positive, negative slope, positive, negative slope. That's what a line is going to look like in high dimensions. If points are exactly on a line, no matter what the dimensionality, it'll look like a line in any of the 2-dimensional coordinate systems, or at worst a point. It'll look like a point if they all happen to have the same values. So you'll see a line is going to be marked by that much of the parallel lines, or all parallel lines, or all crisscross lines where they have a point of intersection. And if it's near a line, if we were to jitter that, you'd see it's nearly that. So you get some sense of, the beautiful thing about a line is that it looks like a line no matter which projection you're looking at. A line in high dimensional space. I mean a straight line. Here's another line. This one looks like it's a positive slope in every pair but one of these axes, where it's a negative slope. Again, that's what a straight line looks like in 7D. So here's something that looks a little different. And if you follow each color, you'll see that same sort of behavior. There's a pinch, I'm following the blue now, there's a pinch point here, spreading out. They're all kind of converging beyond here, so that's a line. Pinch point there, all sort of converging here outside of to the left of dim 4. Between dim 4 and dim 5, they're converging to the left. Between dim 5 and dim 6, they're converging to the right, and so on. Every one of those colors is a line. Okay, so what we actually have are 5 different lines in 7-dimensional space. See that beautiful pinch point construction. Okay, does that make sense? Yes, no? Nod, shake your head, blink your eyes. Does that make sense? So if you follow any one of these colors and follow those rules about what a line is, you should discover that it's a line. It's not going to be like this, because this is a single, in every dimension, the line is covers the whole range of that value. And these lines do not cover the whole range because there are a bunch of lines, 5 different lines in the space. So the blue line is really only in this part on the here, and this olive green line is down in the other part of that dimension 3. So those are 5 lines. Again, make sense? Okay. So here's an interesting structure. This is a 3D helix, a spring. It's a 3D spring that I've embedded in a 10-dimensional space. And so what are you seeing? You're seeing a lot of structure, clearly. And the structure looks like a series of lines, right? So you see wherever there's a joining together, that looks like there's a line there that's going negatively sloped, lines that are going positively sloped. And you can imagine if you have a spring in 10-dimensional space, or to make it easy, think about it in 3-dimensional space, and you're looking at any pair of coordinates. At any projection, it's going to look like a series of lines, right? If you're looking at it side on, the spring, as it's going around, it's going to look like some lines, so you're going to see bunches of lines there. If it was completely end on, so you're looking at it looks like through the cylinder, it's going to look like a circle, which we know it's going to see some sort of curvature. So what you're seeing here is this obviously quite regular structure, not like any real data, but a mathematical object here that's following all of these lines around or near lines in any of the projections. And you see that these particular projections are showing a lot of the lines. You're seeing a lot of the edges of the helix. Okay, very pretty. And there's a paraboloid, which we saw before when we were doing the point line duality. And it's again distinguished by that nice smooth curvature that we see here, imagining following the tangents of the parabola into space in the Cartesian coordinate system. Okay, any questions? Here's a paraboloid in 6-dimensional space. And again, you're getting some hint by seeing a bit of the smooth curvature on the edges, but it's a lot more difficult to assess because it's a 6-dimensional paraboloid. But in some projections, some of the parabola structure is appearing. So this kind of smooth thing, if it's that smooth, it's indicating a very smooth curve in that projection. Here is another structure that's very familiar to you in 7-dimensional space. This is a 2-dimensional hyperplane. Okay, so it's a 2D subspace. Points are only on that 2D subspace within the 7-dimensional space. And if you think about this, again, we only have a 3D world to think about, but think about a plane in 3D, a sheet of paper, right? It's going to look like, so imagine it's on a square. So depending on its orientation, it may look like a diamond, which makes it kind of look like near a line, some sort of correlation. If you see it edge on, it's definitely a line. If it's nearly edge on, it's near to a line, etc. So that's what you're seeing here. Different views of this square in this 2-dimensional square in 7D space. So this is nearly edge on between these two dimensions, okay, and a negative thing. This is nearly edge on, but more a positive slope. This is, not so good. We're not anywhere near the edge. They're kind of spread out. Hard to tell. So you can tell in this projection, it's near line. So a plane would look like that. And you can have more and more fun if you take particular geometric objects and embed them. So the parallel coordinates for nice mathematical objects. Any questions on that? We're going to look at real data in a minute. Real data is not going to be anywhere nearly as nice, right? Because there's going to be noise. Okay, so what you might do, instead of just following this curve you might treat it and fill the area underneath the curve. So it looks like each curve, instead of being a curve, looks like a little mountain range in silhouette. And so that suggests glyphs. So here's, again, I've got this code on the website that I've adapted from some code from a friend of mine, Dan Carr, and calls these mountains. So he's produced some nice little bars to show you, by color you can see which variant we're talking about. And that's essentially a parallel coordinate plot, but with the area given below and some nice axis in the background so you can get some sense of the magnitude and the colors identifying the variants. To be the same sort of thing, can you group these different glyphs together? In any particular glyph, it's a little easier to read what's happening. Of course, there are only 4 variants in this case. So that's a nice way of getting glyphs. So you can use these things to produce glyphs, parallel coordinates. Again, probably by filling in the area since you're just following a curve. That make sense? Okay, I'd like to explore this a little bit, just to take our time here and imagine that we're actually doing an analysis.